Alright students, welcome back. I am posting a short video on LeChatelier's principle in equilibrium so that you guys can use it to prepare for your test tomorrow. It seemed like you guys had this pretty well in class, but I just wanted to make sure that you understood completely and that you had a source of reference in case you got confused. So, to start, let's talk about LeChatelier's principle, which will be the primary focus of this video. LeChatelier's principle says that whenever an equilibrium is put under stress, the equilibrium will respond by shifting towards products or reactants, so either making more products or making more reactants, in order to relieve the stress. So whatever we do to an equilibrium, it will respond by wanting to do the opposite. And we can use that to reliably predict which way we can force an equilibrium. Before we get too far into that, let's just refresh our definition of an equilibrium. And that definition is a state in which the reactants of a reaction and products are both being formed at the same rate, leading to no net change. And we know that any chemical reaction that we write is in fact an equilibrium, and that when we mix chemicals, those chemicals are going to proceed until they have reached that state of equilibrium, and that signifies sort of what we see as the end of the reaction, because we would stop seeing chemical change at that point. So all reactions are trying to reach equilibrium, and when that happens, our products and reactants will be forming at the same rate. So let's take a look at our classic example at our Haber process, where nitrogen reacts with hydrogen in order to form ammonia. So when this reaction is in equilibrium, which is signified by this double reaction arrow right here, that means that every time we form two new molecules of NH3, those two molecules of NH3 break back down to form nitrogen and hydrogen. And so as quickly as we're forming this product, ammonia, the ammonia is breaking back down to form reactants. So we keep cycling between these and kind of spinning our wheels and going nowhere, which is equilibrium in essence. So what LeChatelier's principle says is that once this is at equilibrium, we can force it in one direction or the other by putting a stress on the equilibrium. So many of the LeChatelier's principles break down to what these different stresses are and how they are affected. And the way that I have broken this down is by making this sort of table, which you can feel free to use on your exam tomorrow, but it just kind of summarizes the thought process very concisely. So we're going to start with the assumption that this is at equilibrium, and then we're going to put a stress on the equilibrium and figure out what happens. So let's take a look at this, these stresses. So the first stress we're going to do is we're going to increase the concentration of nitrogen. So if we increase the concentration of nitrogen, the equilibrium is now disturbed. It was at equilibrium, and now we've increased the concentration of nitrogen. The equilibrium wants to respond to our stress by doing the exact opposite. If we increase the nitrogen, the equilibrium wants to bring the nitrogen concentration back down. The only way that it has to do this is it will take the extra nitrogen that you added and it will convert it into products. It will convert it into ammonia. So the way this works is, since the equilibrium wants to decrease the concentration of nitrogen, it will move in this direction away from nitrogen. So the equilibrium will shift to the right towards products. So the same thing would be true if we increase the concentration of either side. So if we increase the concentration of a product, if we increase the concentration of NH3, the equilibrium would shift in the opposite direction in order to use that NH3 up. So if we increase the concentration of something, the equilibrium will shift away from that thing to make less of it. And the exact opposite will happen if we decrease the concentration of something. Let's say we decrease the concentration of hydrogen. If we decrease the concentration of hydrogen, suddenly the equilibrium will see that we have less hydrogen than we had at equilibrium, so the equilibrium is disturbed. So it sees the decrease in hydrogen, it wants to do the opposite. It wants to bring the concentration of hydrogen back up. The only way for the equilibrium to make more hydrogen is to shift in that direction, is to fill the void by making more hydrogen. So a decrease in the concentration of H2 will cause a subsequent increase in the concentration of H2 from the equilibrium shifting in that direction, and that will cause the equilibrium to shift to the left, towards H2, or in general, towards reactants. So that's one way we can stress an equilibrium, by either increasing or decreasing the concentration of the products or reactants. The other two primary ways we can stress an equilibrium is by changing the temperature or by changing the pressure. So let's go through temperature first. Whenever we are dealing with a temperature change, LeChatelier's principle still holds true. Let's say the stress on this equilibrium will be that we've increased the temperature. The way the equilibrium will respond is by doing the opposite. The equilibrium will respond by trying to bring the temperature back down to where it was when we were at equilibrium. The way it will do that is it will need to create less heat in the reaction. So whenever we're given any problem involving temperature, we need to figure out where is the heat. Is heat a reactant or is heat a product? In order to determine that, we need to know whether the reaction is exo or endothermic. In order to determine that, the primary way we do that is we'll be given what's called a delta H value, which will tell in which way the energy has changed over the course of the reaction. Negative delta H means exothermic, whereas positive delta H equals endothermic. In an exothermic reaction, energy is leaving. Energy is being created as the reaction progresses. In an endothermic reaction, energy is being drawn in. It's needed for the reaction to progress. So, if we see an exothermic process, that means heat is a product. If we see an endothermic process, that means heat is a reactant. So, in this case, we look at this and we're given a delta H value of negative 91.8 kilojoules. That means every time we go through this reaction once, we create 91.8 kilojoules of energy on this side. So we're making heat on this side of the reaction. Whenever we're given a problem involving temperature, it's important that we figure out on which side of the reaction heat goes. So if heat is on this side, in response to us increasing the temperature, the equilibrium wants to bring the temperature back down, and it will do that by moving away from heat. So if the equilibrium needs to bring the temperature down, it moves away from heat, and in this case, that is a shift to the left, towards reactants. So, in order to do a temperature problem, we have to know whether the reaction is exothermic or endothermic. We put heat into the reaction, and then we determine in which way we need to go in order to affect temperature in the way we need to. In this case, we needed to bring temperature down, so we moved away from heat. If we needed to bring temperature up, we would move towards heat. For pressure, for changes in pressure, what we need to do is we need to determine where the gases are in the equation. We only count gases because gases are the only state of matter that's legitimately affected by pressure. So in order to do that, what we do is we look at the reaction and we determine how many moles of gas are on each side. We don't count solids, liquids, or aqueous solutions when we're taking this into account. So in order to add up the moles of gas, we look at the coefficients on each side of the reaction. For each reaction cycle, we have 1 mole of nitrogen and 3 moles of hydrogen for a total of 4 moles of gas on the reactant side. On the product side, we only have 2 moles of gas. So what this means is that we have less gas molecules on this side of the reaction than on this side. Every time we convert reactants into products, we make less gas. And in making less gas, it's sort of like letting air out of a tire. We're decreasing the pressure by moving in this direction. And alternately, we're increasing the pressure moving from products back to reactants, moving in the reverse direction. Because we're making more moles of gas, we're adding more air to the tire. So let's look at the stress and see what happens in this reaction. If we increase the pressure on this reaction vessel, for example, if we were to decrease the volume and squeeze this reaction vessel and increase the overall pressure, The equilibrium's response would be, whoa, you increased the pressure? Okay, I want to bring the pressure back down because I was happy because I was at equilibrium and you disturbed that. So if the equilibrium wants to decrease the pressure, the way it will do that will be in moving in to the right. It will move in the direction of less gas. Less gas on this side of the reaction, so the equilibrium will move to the right towards products. So any question that involves pressure, we need to figure out which side of the reaction has more or less gas. We need to figure out what the equilibrium is going to do in response, and then we need to move in the direction that accomplishes that. The final thing that we can do, which is sort of an equilibrium stress, sort of not, is we can add a catalyst. If we add a catalyst to a reaction, it will speed up the reaction, but it will speed it up in both directions, both towards products and towards reactants. So if we add a catalyst, the equilibrium response will be none. It will not create any more products and it will not create any more reactants. The end result is that if you were making products and then reactants and then products and then reactants at that rate that was even, the rate will stay even, it'll just move far faster. So you'll get products, reactants, products, reactants, products, reactants, products, reactants, but there'll be no net change on the equilibrium from an added catalyst. Okay, I hope that helps. Utilize this video for your exam tomorrow, and I will talk to you tomorrow. Good luck on your test.